All right, so we're talking 11.1. So in 11.1, we are talking about this funky thing called chi-squared goodness of fit test. Now, here's the first thing is understand that chi-squared that's a Greek symbol, chi, and we're literally squaring it, right? So on this, what you need to know is that we are always, or chi-squared is always trying to see, is what I actually observe too much different from what we are hoping to see? That's what it is. So right now, we're going to work on a function called goodness of fit. So we're going to say something like this. Does this data set here, is it a good fit if this is truly what we believe is out there, right? So that's what we need to look at here. So here's how we're going to do it. I'm actually going to redo this. I'm going to do a Republican, Democrat, Green Party, let's call it Reform, and Other, right? So these are my groups. And so I want to see in this table format, I want to see what is actually observed. What are the numbers that we actually observe? Okay, so let's see this 197, 153, 32, 12, and 6. Those are actually observed. But what numbers would we expect to see? Now, check out what they did. They told us that 48% should have been Republican, 43% Democrat, 4% Green, 3% Reform, and 2% Other. So if I looked at everybody in here, it says that N is equal to 400, right? It says right here, 400 voters surveyed. If you add all these up, it should equal 400. So out of 400. So in this spot, the actual, or sorry, it's expected is actually what we call it. The expected counts, right? What if I took 48% times 400, right? I'm going to do that in my calculator real quick. If I do 0.48 times 400, looks like I should expect to see, if truly 48% are, then I would expect to see 192 of 400 to be Republicans. Well, what about Democrats? Democrats is 0.43 times 400. Okay, so I'm going to go 43 times 400. And so I would expect to see 172. And then 0.04 of 400, well, that's the next, right? That's the Green Party. So 0.04 times 400. 16 should be there. 0.03 times 400. Then kind of get the, right, how the rest of it goes. Reform, and then 0.02 times 400, and I get 8. So here's what I would expect to see if those numbers were correct up there, but this is what I actually observed, right? Because this is what I call observed versus expected. Okay, let's go through it. Now, this is based on the video that you should have watched previous. Since we are running a test of significance, then I am thinking phantoms, okay? And then, most importantly, the H, the A, the T, the O, the M, all right? What are they? So, null hypothesis, here we go. So the null hypothesis is always going to be that my observed is equal to the expected, or in a sense, that we would expect the probability of Republicans to equal 0.48. So I'm literally just writing this out instead of writing words. A probability of Democrats should equal 0.43. Now, just let me take note that I could say it in words if I wanted to. I could just write out a bunch of words here. But I like probability. I like showing what's going on if this is the case. So then the probability of other should equal to 0.2. Right, so this is what we're looking for, 0.03, okay? Alternatively, this is always going to be standard no matter what chi-squared you're doing. If we're doing a goodness fit, we're going to say at least one proportion is different. At least one proportion is different. At least one. Now, they could all be different. We don't care as long as one of these proportions is different. And by different, we mean way different, not just kind of different there. Okay? All right, so let's do that's the H part of phantoms. Let's do the A part of phantoms. The A part of phantoms always comes with 3 parts. And you know this because we've been doing it since chapter 8. So it comes with a shape check. So we want to check that check that our shape we can use the chi-squared shape. So here it is. It's a simple one. Are all expected counts greater than or equal to 5? Are all expected counts greater than or equal to 5? Well, let's go look. 192 is, 172 is, 16 is, 12 is, 8 is. That's a big fat yes. Good, okay. Number 2, is it random? Well, let's go up here and check. Let's see. Random sample of 400 voters. So, yes, that is. And number 3, 10% rule, right? We take 400 voters. So, are all voters, is there greater than or equal to, multiply your 400 by 10, 4,000. Is there more than 4,000 voters out there to choose from? I think so. Right? What do you think? I think that's kind of what we have to go with. But it's usually going to be assumed that that's the case. Okay. All right. The T part of phantoms. Here we go. So this is a chi-squared. So remembering from the video, a chi-squared graph is always going to be skewed right. And yeah, it's no longer that normal symmetric shape like a normal curve, or a T curve would be a normal shape. It's always going to have a lot of data on the left and a little bit on the right. Now, it may not look perfectly, there could be even more severe skew than this, but it is going to be severely skewed. A 0 here, that meaning that there would be no difference between what is expected and what is observed. So let's take a look at the chi-squared formula. The chi-squared formula, if you look at your formula sheet, it is the summation of the observed minus the expected squared divided by the expected. And now summation means go to the next one, observed minus expected squared divided by expected, and then the next one, and the next one, and the next one. So this is what it looks like on this one. So let me kind of fold this in here. So observed, so we observed for Republicans 197 minus the expected 192 squared over the expected, so that's 192, plus the next one we're going to go 153 minus what's expected to see, 172 squared, that's going to take away the negatives, that's why they square it, divided by 172 plus dot dot dot, and we're going to keep going until we find that. Okay. Now, also what you need to take into account is degree of freedom. Degree of freedom for everything we've done so far is all about how much sample size, right? It's been, sample size -1. No longer in chi-squared. Chi-squared is about how many categories. We've got 1, 2, 3, 4, and 5. We have 5 categories. We're going to subtract 1 from that. So our degree of freedom for this one is 5 categories minus 1, a degree of freedom is 4. So if we needed to go look this up, we have a chi-squared table on our formula sheet. We could use the chi-squared table. We would go to the degree of freedom 4, and we'd slide across until we find our chi-squared value to find the p-value if we wanted to. But we also have calculators, folks. So let's go in our calculator. Let me sidestep this real quick. Here's where I'm going. I'm going to stat, then I'm going to go to test, and then I'm going to go to chi-squared GOF. Chi-squared GOF. Make sure you go to the GOF section now, because if you do the other one, that's going to be for the next day. Okay, so GOF. But in order to do this now, here's what we need to do. We need to put our observed values in L1, and we need to put our expected values in L2. So let's do that first. So I'm going to quit out of this. I'm going to go to Stat. I'm going to go to Edit. L1, clear that list. L2, clear that list. And let's start fresh. Here we go. 197, 153, 32, 12, and 6. And then in L2, 192, 172, 16, 12, 8. Okay, make sure they line up, right? Observed and expected should have the exact same amount. Okay, now that we're there, here I go. Let's go back to this. Quit out of this. Stat, test, chi-squared GOF, way down. Mine is a D there. test. Observed values are in L1, so I'm going to do my observed. Yep, they're in L1. I'm going to do my expected. Yep, they're in L2. Degree of freedom, well, we had to figure that out. What was it again? Remember, categories minus 1, so it's going to be 4. So I'm going to put 4 there, and then I am going to calculate in there. It's going to give me everything I need. So check this out. As I'm doing this right here, equals 18.73. All right, 18.7. That's the chi-squared value. That's each component being added together to give me 18.73. Now, where is this on the graph? I don't know, but it's over here somewhere, 18.73. And if I shaded this, it's barely going to shade. You know why? Your p-value tells you how much of the graph you shaded. P-value, mine says 8.88. Keep looking, e to the negative fourth. So really, we're talking about 0.000888. That is super tiny. So what kind of decisions do we make? You know how to do this now. P-value versus alpha value. If my p-value is less than your alpha value, then we will reject. Let's see what they said on this. They didn't even give me an alpha value. That means I get to make up my own. Alpha equal to, let's say, 1%. In that case, we would reject the null hypothesis. So in conclusion, that means at least one proportion is different. So then does the data provide evidence that voters in the election did not vote according to their registered affiliation? We would say we have evidence to suggest that voters did not vote according to their affiliation. Right? That's what it means to reject. When you reject, we have evidence to say the alternative, which is at least one proportion is different, which means somebody didn't vote according to their affiliation. Now, how do you figure this out? Now look in my calculator, there's this thing, it says CNTRB. That means contributions. So we can look at each of these different values, and guess what? There is 5 different values. And scroll, hit your side arrow button, and you scroll. The first number I see there is 0.13, and then 2.09, and then 16, then 0, then 15. So that one, 16, 0.5. This group right here, the third group listed, is basically saying is the biggest contributor to the rejection. The third group listed here, right? So we observed 32 Green Party people, but we only expected to see 16. That is double. That is the biggest proportional difference out of all of them. So the Green Party, you don't necessarily have to write this, but sometimes they'll ask the follow-up question. So I'm just telling you right now, the Green Party is the biggest contributor. Right? Green Party. Again, how do I find it? Look at the contributions, whichever number is listed. And these are for each of the 5 categories. Whichever one's the biggest contributor, it is leading to the rejection of the null hypothesis there. Okay, that's just some good side information. All right, let's go to the next one here. All right, Human Resources Department, very large corporation, more than 20,000 employees, suspects that people are more likely to call in sick Monday or Friday, so they take long weekends. Took a random sample of 850 sick day reports from the past few years and determined the day of the week each report. Here's the results. Do the data provide, anytime you hear this, do the data provide convincing evidence? You're thinking phantoms. Okay. That sick day calls are not evenly distributed. Here's the suspicion, not evenly distributed through the week. Justify your answer. So remember, we always have an equal to for the null and then something else for the alternative. So the null hypothesis on this one, getting right into it, we would say that all the days should be evenly distributed and the alternative is going to be not evenly distributed. So this is what I would do. I like this. Probability of Monday equals the probability of Tuesday, which equals the probability of Wednesday, which equals, I guess, proportion is what I should be saying. Proportion of Thursday, which is the proportion of Friday. We would expect to see sick days be the same if people just randomly took off sick days or people just randomly got sick. But we are saying, here's the keywords again, at least one day's proportion is different. Is different, right? So at least one is different. We don't care which one. What we're going to come back and suspect that probably Monday or Friday. That was kind of in the original suspicion up here. Okay, assumption checks. Here we go. We got to do the shape check. Number one, can I use a chi-squared? Well, we need to know, are all expected counts greater than or equal to 5? I don't know. I don't see any expected counts. So this is the actual observed that we see here, the observed. So let's just do the expected right underneath, expected, right, underneath each of these. So I'm just going to create this next expected. So if we're going with this null hypothesis that they're all the same, essentially what we're going to do is take the 5 days of the week. There was 850 sick days, right? They just told us right here, 850 sick days divided by 5 days. So let's do that. 8 in my calculator. 850 divided by 5 days a week, 170. So if they were all the same, I would expect, right, because we always based on the null hypothesis, I would expect to see 160 sick, 170. Sorry, I'm saying that. 170, 170, and 170. Right? That would be the expectation of that, right? So are those expected counts greater than or equal to 5? Absolutely, way bigger. Number two, it does say a random sample, right? So random sample, check. And number three, did we have at least, so we're going to say sick days, right? So just sick days in general that were taken off. Is it at least 8,500 sick days? And since there's more than 2,000 employees, and let's just imagine every employee takes 2 sick days a year, and that's way conservative, but then that's 40,000 sick days available. So yeah, this is a safe assumption. All right, let's do the T part. That's the test calculation and statistic. Let's draw our chi-squared graph. It always starts at 0 here. Let's do chi-squared equal to, let's start the formula. So it's observed 192 minus expected 170 squared over 170 plus, what do we got? 151 minus 170 squared divided by 170 plus dot, dot, dot equals, time for my calculator. Let's go. So stat, edit. First thing we got to do, put our data in. L1, L2, observed in L1. So that's what I'm doing right now. And then I'm going to put my expected in L2. Okay, that is done. Now, I'm going to go for it here. Stat, test, go all the way down to GOF test, L1, L2. How many? We have 5 days, right? 1, 2, 3, 4, 5. So we do know that our degree of freedom here is going to equal 5 minus 1, so it's 4. So make sure I put a 4 in there. Calculate. And here we go. I'm just going to fill in some info. 17.78. Well, that's going to be over here, 17.78, because it's away from 0. I would shade. I'm going to go ahead and obtain a p-value. That p-value is going to be 0.001365. All right, small p-value. Again, no alpha value given, so let's just make our own decision. You choose. But I'm going to go ahead and say my p-value is less than alpha, which I'm going to set, again, at 1%. So in that case, I'm going to reject the null hypothesis. Summary. What does that mean? That means we have evidence to suggest that people don't take sick days evenly across the week. And then we could go further into suspicion. Which day of the week contributes most? Which day of the week contributes most? Go to your contribution list right now. 2.8, 2.1, 2.8, again, 1.9, 8 point something. The last day, Fridays, is the biggest contributor to not being equal. Fridays, which sounds like, so if I go back and do some analysis on this, people take more sick days on Fridays than any other day of the week. Go figure on that. Okay, so there you go. 2 phantom problems, chi-squared, goodness of fit test. Use your chi-squared GOF test in the calculator. That will help you get through your Khan Academy's My Open Maths, but then also check out all these other things.